Our sun is so big that 1,000,000 Earths would fit inside it. Now hold that thought for a second, because there is a star out there so vast that our sun would be a single grain of sand next to it. Swap it in for our sun, drop it right into the center of our solar system, and it would swallow Mercury, then Venus, then Earth, then Mars, and it would keep going, reaching almost all the way out to Saturn. Even light, the fastest thing in the entire universe, would need most of a day just to travel once around it. This is the story of the biggest things we have ever found, and it is also the story of a strange rule, written into the laws of physics themselves, that says one of these stars should not be able to exist at all. Not, we can't explain it. Not, it's rare. The math said it was impossible. And yet, there it is, burning in the sky. To understand how big we're really talking about, and why one of these giants breaks the rules, we have to start with something familiar. We have to start with home. Here is our planet. Everything that has ever happened to our species happened right here, on this single blue dot. Now let's bring in the sun. The sun is about 109 times wider than the Earth. If the sun were a hollow ball, you could pour roughly 1.3 million Earths inside it, and still have room to spare. It is not just the biggest thing in our solar system. It is more than 99% of everything in it. Every planet, every moon, every asteroid combined is barely a rounding error next to the sun. And the sun is enormous in a way that's hard to feel. So let's make it real with light. Light travels 300,000 kilometers every second. At that speed, it could circle the entire Earth about 7.5 times in one single second. Now point that same beam of light at the sun and send it racing around the outside. How long does it take to go all the way around? About 14.5 seconds. Hold on to that number. 14.5 seconds for light to lap our sun. We're going to come back to it, and when we do, it's going to sound almost quaint. So the sun feels like the ultimate giant. But on the scale of the galaxy, our sun is average, ordinary, a perfectly normal yellow star, one of hundreds of billions. To find the real monsters, we have to leave the sun behind and look for a very particular kind of star, a dying one. Because the biggest stars in the sky, the ones measured by sheer width, are not young and healthy. They are old, swollen, and running out of fuel. And the first one on our journey is a star you have almost certainly seen with your own eyes. Look up at the constellation Orion, the hunter, and find his shoulder. That reddish point of light is Betelgeuse. It's a red supergiant, and it is dying. As stars like this run low on fuel, their outer layers puff up and cool, and they balloon to staggering sizes. Betelgeuse is our best estimate at around 760 times the radius of the sun. So do the swap again. Take out our sun, drop in Betelgeuse. It would engulf Mercury, Venus, Earth, and Mars, and its surface would reach out almost to the orbit of Jupiter. The ground you're standing on would be deep inside the star. And yet, Betelgeuse is only the warm-up. It's the star that shows us the pattern. Because if a dying star 700 times wider than the sun can hide inside Jupiter's orbit, the obvious question is, how far does this go? How big can a single star actually get before something stops it? To answer that, we have to leave the familiar sky behind and go hunting for the true hypergiants. And this is where the numbers stop feeling real. Deep in the constellation Canis Majoris sits a star called UY Canis Majoris. It is a red hypergiant, and it is one of the largest stars we have ever measured with confidence. Our best estimate puts it at around 1,400 times the radius of the sun, put it where our sun is, and its surface wouldn't stop at Jupiter. It would swallow Jupiter whole and keep going. Now remember that beam of light, the one that lapped our sun in 14.5 seconds? To travel once around UY Canis Majoris, that same beam of light would need about 6 hours. 6 hours. Think about what that means. If you could somehow stand on the surface of that star and send a flash of light racing around the equator, you could eat breakfast, go to work, sit through half your meetings, and the light still wouldn't have made it back to you. On the sun, That trip took 15 seconds. Here, it takes most of a working day. That is not a bigger version of the Sun. That is a different category of object entirely. And believe it or not, WOH Canis Majoris is not even the record holder. In late 2024, something remarkable happened. For the first time in history, astronomers captured a detailed, close-up image of a star outside our own galaxy. The star is called WOH G64, and it lives in the Large Magellanic Cloud, a small companion galaxy about 160,000 light-years away. Using the Very Large Telescope in Chile, the European Southern Observatory saw it directly, and what they found was a behemoth. Roughly 2,000 times the radius of the Sun, wrapped in a strange, egg-shaped cocoon of gas and dust that it is coughing out into space. Because WOH G64 is dying, and it is dying loudly. Let that sink in. We took a photograph of the surface of a single star in another galaxy, 160,000 light-years away, and it filled the frame. That's how big these things are. But there is one more star that has, at times, worn the crown for the largest ever measured. And its name is Stephenson 2-18. Stephenson 2-18 is our best estimate at a staggering 2,150 times the radius of the Sun. If you dropped it into our solar system in place of the Sun, its surface would push out to somewhere around the orbit of Saturn. Mercury, Venus, Earth, Mars, Jupiter, all of them, buried deep inside a single star. And that beam of light, the one that circled our Sun in 15 seconds? To go once around Stephenson 2-18, it would need the better part of a full day. This is the star that gives our title its promise. A star so big, light takes hours to cross it. So we have our answer, right? Stephenson 2-18 is the biggest star in the universe. Except, here's the twist. It might not be. Because these numbers, every single one I've given you, are not measurements carved in stone. They are our best estimates, and estimates can change. These stars are so far away, so shrouded in their own dust, that measuring them is fiendishly hard. And every so often, the record doesn't just get beaten, it gets erased. For years, the reigning champion, the star at the top of every largest stars list, was UY Scuti, thought to be around 1,700 times the radius of the Sun. It was famous. It was in the textbooks. And then better data arrived. Using the Gaia Space Telescope, which measures the distances to stars with breathtaking precision, astronomers took a fresh look. And they realized UY Scuti was closer than we thought, which meant it was smaller than we thought. Not by a little. Its estimated size collapsed to somewhere between 700 and 1,100 solar radii. The king was dethroned, not by a bigger star, but by a better ruler. And that tells you something important about how science actually works. We are not reading these sizes off a label. We are inferring them at the very edge of what our instruments can do and correcting ourselves as the data gets sharper. So when I say a star is the biggest we've ever found, what I really mean is, it's the biggest we've measured, so far, with the tools we have today. But now I need to let you in on a secret. Because for all their jaw-dropping size, these hypergiants are hiding something. And it completely changes what big even means. Here's the secret. These red hypergiants, for all their unimaginable width, are almost nothing. They are enormous, but they are shockingly light. A star like this might contain only 10 to 40 times the mass of our Sun, spread out across a volume so vast that the outer layers are thinner than the air you're breathing right now, thinner than a laboratory vacuum. If you could fly a spaceship into the outer edge of one of these giants, you might barely notice you'd entered a star at all. They are less like solid balls of fire and more like glowing red clouds, dying, bloated, and almost empty. So being the biggest by width, it turns out, is not the same as being the biggest, full stop. Which brings us to the real monster. The star that doesn't break records for size, but breaks the actual rules of physics. To find it, We have to stop asking which star is the widest and start asking a much more dangerous question. Which star is the heaviest? Because there is a hard limit on how heavy a star is allowed to be. A ceiling written into the laws of nature. And nature, it seems, doesn't always respect its own ceiling. Here's the rule. The heavier a star is, the more furiously it burns. And the brightness doesn't rise gently with mass, it explodes upward. Double a star's mass, and it can shine roughly 8 times brighter. And that brightness is dangerous, because light itself pushes. The flood of radiation pouring out of a massive star's core physically shoves its outer layers outward, fighting against the gravity that holds the star together. Pile on enough mass, and the radiation wins. The star starts blowing itself apart from the inside. Physicists call this tipping point the Eddington Limit, and for decades the math suggested no star could survive being born much heavier than about 150 times the mass of the Sun. Any bigger, and it should tear itself to pieces. Too bright to exist. And then we found our 136A1. It sits inside a churning stellar nursery called the Tarantula Nebula, in that same large Magellanic Cloud. And it is a monster of a completely different kind. Today, our 136A1 holds roughly 265 times the mass of our Sun. And here's the thing, it was born even heavier, closer to 320 solar masses, and it has been shedding mass ever since, blasting the equivalent of dozens of suns out into space on a scorching stellar wind. It is the most luminous star we know of, shining with the light of nearly 9 million suns. And it sailed straight past the 150 solar mass ceiling that physics said could not be crossed. So what happens when a star breaks the rules? Do we throw out the star, or do we throw out the rule? We rewrote the rule. Our 136A1 didn't cheat physics. It taught us that our ceiling was too low and forced astronomers to redraw the line for how massive a star can be. And that, in the end, is the real punchline of every giant in this video. The star so wide light needs hours to cross it, so heavy it shouldn't exist, so distant we can barely measure it. Every number here is our best guess, at the very frontier of what we can know, and we are still refining every single one, with new eyes like Gaia and the Very Large Telescope. These stars sit right at the edge of what the laws of physics will allow, and every time we look closer, the universe turns out to be stranger and bigger than we dared to imagine. Now, some of these giants don't just die quietly. Some of them collapse into something that swallows light itself. And believe it or not, we've actually recorded the sound one of them makes. Go watch the sound a black hole makes. NASA recorded it, and let the universe sing to you. We'll see you in the deep field.